Great, perfect. So I want to start first by minimizing this. I'm all set. Okay, fantastic. So I'd like to start by saying thanks to Luca and more generally to the Warwick Maths Society for inviting me to give this talk. It's a pleasure. Maybe a shame it's online, but you know, it is what it is. And I'd like to talk to you a little bit about money, or at least that's how I've baited you all in to doing this talk, to coming to this talk. Now, I'll start just by saying that the slides will be available after, so um, feel free to look at them. And from what I understand, it's being recorded, so you can rewatch me at night to go to sleep whenever you want. It'll be available to you. Any questions, please do ask, unmute yourself or use the chat. Unmute yourself would be better because it's easier to ask a question. Otherwise, through the chat, I'll pause at the end of each section as well to have a longer moment to take questions. And also, if you can't hear me or see me, then please do let me know. Also, if I look to my left, it means that I'm looking at my tablet and I can see what I'm sharing. So if I look to my left, I'm not looking away. You'll just have to excuse me for that. So let's get going. I'm going to start by talking a little bit about congruent numbers. I imagine you've read the abstract, but let's see what they are. So a natural number n is a congruent number if, well, it's the area of a triangle with side lengths A, B, C. And this triangle should be a right-angled triangle, and the side lengths are rational numbers. Now, the study of these numbers has an extremely long history. It dates all the way back to Diophantus in the 3rd century. Then there was a bit of a gap. Some Arab mathematicians in the 10th century looked at it. And then you had people like Fermat and Euler and many other big names who kind of considered this problem. It was viewed as a fundamental problem in number theory, let's say, and many more. So many people have looked at this. I'm not going to go into the history any more than that. I want to talk to you more about the maths behind this. Let's see an example. Let's take the classic right-angled triangle where we set our side lengths to be 3, 4, and 5. Looks like this. I'm sure you've seen this before. What's the area? We're interested in the area of this triangle. Well, it's half base times height. So it's 3 times 4 over 2, which is 6. And so by definition, 6 is a congruent number. Great. And we want to do this for more numbers. And so you pick another number, let's say 3, and you ask, is 3 a congruent number? And remember, the triangles you want to construct should have rational side lengths. Here, the side lengths are whole numbers, but this should work for any rational number. And you try a few out and you say, well, I can't do it. But, you know, that's not a proof. And you try loads and you say, well, it really doesn't seem to be working, and so you say it's not a congruent number. But if it isn't a congruent number, I want a proof. So if it isn't, then why isn't it? If not, why not? And so this is kind of the million-dollar question, which has attracted you to this talk. So given n in the natural numbers, is n a congruent number? And give me a way that I can test this for n, which could be really, really big. So maybe you can get a method of doing it for something like 3, which works, but then I give you 100 or I give you 1,000,000, and I want you to be able to tell me whether n is congruent or not. And if a certain conjecture holds, and we'll see this near the end of the talk, if the Birch and Swinnerton-Dyer conjecture holds, then we can indeed give a way of testing whether n is congruent. And the prize for this, so this BSD or Birch and Swinnerton-Dyer conjecture has a prize of $1 million because it's a Clay Institute Millennium Prize problem. There were 7 of these problems. They were posed in the year 2000. And if you solve it, you get $1 million. Well, actually, I mean, given that if you now, a member of the audience, goes ahead and solves this problem, then it would be only fair that I take a 10% commission. And so you will actually win $0.9 million. But I mean, it's a pretty good payday all the same. And maybe a little thing to note at the end is to say, don't be a Perelman, because Grigory Perelman solved one of these 7 Clay Institute Millennium Prize problems, and he refused the money. And he also refused a Fields Medal. So if you take one thing from the talk today, is take the money when you're offered it, and give me my 10% too. Now, let's get into some more serious maths. Let's make some first observations. So we're dealing with a right-angled triangle with side lengths ABC, and let's suppose that n is a congruent number. And so we only really know 2 things. N is the area of this triangle, so n is AB over 2, half base times height, and the triangle is right-angled, so a squared plus b squared equals c squared, the Pythagorean identity. And as I've said, these side lengths should be rational, so a, b, and c are rational numbers. Now, people have had a long time to play around with these 2 equations, which are really, so these 2 equations up here, which are really all we know. And so you can start noticing some few things. I mean, in particular, we have these 2 identities. A plus b over 2 all squared is c over 2 all squared plus n, and similarly with the pluses replaced by minuses. And I guess what you do at this point is you notice something rather peculiar. If I set x to be the term c over 2 all squared, then what we note is that x minus n, x and x plus n are all squares of rational numbers. And so I'm just going to call them squares or rational squares. Right, you can see that x is c over 2 all squared, so that's a square. And similarly, say x plus n from the identity above is a plus b over 2 all squared. Similarly for x minus n. So we found 3 squares in this arithmetic progression. And I guess now that we've found 3 squares, we want to combine the information in some way. And what we can do is we can take the product of these. Now, if you have 3 squares, then the product of these numbers will also be a square. What I'm saying here is that x minus n times x plus n is equal to a square. So it's equal to y squared for some rational number y. So I'm going to change slide now, and I've just repeated what I've done so far. We've got x minus n times x plus n is y squared for some y in the rational numbers, and here x, as I said, was c over 2 all squared, which is also a rational number because c is. And so I want to rephrase this in what might seem quite a weird way if you haven't seen this type of thing before, but I want to consider the point P in the plane, the point P with coordinates little x and little y, and I'm going to say that this is a rational point on the curve En. So the curve En, for any natural number n, I'm going to define it to be this. The curve given by the equation y squared equals x times x plus n times x minus n. Now, when I say that P, which is little x comma little y, is a rational point on the curve, I mean that little x and little y satisfy the equation of the curve, and that its coordinates little x and little y are rational. And how do I write this? Well, I write the set of rational points as E, N, parentheses, Q. And P is a rational point, so P lives inside this set. Now, what do these curves look like? I've put an example here of the curve E6. So I've just set n equals 6 into the above, and I've plotted it. Maybe, you know, the type of thing you might do at school where you just draw a curve in the plane. So that's what that curve looks like. So I've repeated here on the next slide what we've got so far. We've got P, a rational point on the curve En. And I've also written the equation for the curve En on this slide as well. And I want to go even further, so making a further observation, and that is that not only is this a rational point on my curve, but its y coordinate, so this y that we found, is non-zero. And that's my claim. Let's give a quick proof of this. Well, if little y is 0, then from the equation of the curve, we know that x is either 0, n, or minus n. And so c over 2 all squared is 0, n, or minus n. Let's look at each case. Well, if c over 2 squared is 0, then c equals 0. That's a contradiction because c is the side length, namely the hypotenuse of our right-angled triangle, and so it's certainly positive. The next case is slightly harder. If c over 2 squared is equal to n, then from our kind of two equations at the start, you'll find that a and b, the other two side lengths, are equal. And then from the Pythagorean identity, you would see that c squared is a squared plus b squared is 2a squared. But this is a contradiction because c squared is a square, but 2a squared is not a rational square. That also doesn't work. And the last case is quite easy. We can't have c over 2 squared is minus n because c over 2 squared is positive, but minus n is negative. That's also a contradiction. And so I've proven my claim. Y is indeed non-zero. So as a summary, what have we shown? We've shown that if n is a congruent number, the first thing we supposed, then there exists a point, which we construct, little x, little y, on the curve En. It's a rational point, and the y coordinate is non-zero. That's what we've shown so far. So I've repeated that summary at the start of the next slide here. And maybe the most natural question at this point is, what about the converse? And let's be precise about this. I'm saying if I choose a point, which I'm now going to call x1, y1, a rational point on this curve En, which simply means that x1 and y1 are rational and they satisfy the equation of my curve, then and also the y1, this y coordinate is non-zero, I want to ask, is n congruent? Do I have the converse to this summary statement? And well, the answer is yes. The first thing we can do by symmetry is to flip the sign of y1 if it's negative. So if y1 is non-zero, if y1 is negative, then we can take the point x1 comma minus y1, and then minus y1 will be positive. So this is kind of like reflection in the x-axis in our diagram. So we may as well assume that y1 is positive. And then, well, I want to show that n is a congruent number. So all I'm going to do is write down a right-angled triangle. So I want to write down three side lengths. Here they are. Where these come from is a question I'm not going to answer today, but which one can answer where these come from. And let's note some things. Well, x1 and y1 are rational, and n is a whole number. So a, b, and c are going to be rational. You can check, I'm not going to do this, but this is, let's say, a routine calculation, that a squared plus b squared is c squared. So it's going to be right-angled. You can check, again, that if you take a times b and divide by 2, so the area of this triangle, then you get out n, which is what we want. We want n to be congruent. We want n to be the area of this triangle. And, well, the last thing to check is that for this to actually be a triangle, we need to make sure the side lengths are positive. Now, from the third bullet point, if I rearrange that, I get a times b is equal to 2n, which is positive. So if a times b is positive, then either a and b are both positive or they're both negative. Now, if they're both negative, I just flip the signs and make them both positive. So I can assume that a and b are positive by flipping the signs if necessary. And from the equation of c, you can see that c is also positive. And so n is a congruent number. All I've done is I've taken my point on the curve En, a rational point with non-zero y coordinate, and I've constructed a triangle so that a right-angled triangle with rational side lengths so that its area is n, and that tells me that n is a congruent number. So I've proven the converse, and what I've proven is precisely this theorem, which I've called main theorem version 1, and as we go through, we'll see other versions of this theorem. It says that n is a congruent number if and only if there exists a rational point P on our curve with non-zero y coordinate. So I've rephrased what it means to be a congruent number. And so if I want to make any progress, I want to understand the set of rational points on my curve. And you could ask at this point, well, isn't this a harder question? I mean, I started off with two pretty simple looking equations, and it looks like I've kind of made this into something which looks like much more of a mess. And yeah, the answer is kind of, in one sense. But at the same time, this En is a special type of curve. It's not just any old curve, it's a special type of curve. It's actually what we call an elliptic curve. And so we have tools to understand its set of rational points. So although the question looks harder, in fact, it's going to help us. And it brings me to my next section, which is going to be on elliptic curves. So maybe what I'll do is I'll leave the previous slide up just for 30 seconds to help you absorb this main theorem and take a short pause, maybe see if there are any questions at this point. No, check the chat. Right, so there'll be more opportunities to ask questions as we go through. Obviously, you can also interrupt me at any point. So let's talk about elliptic curves. En is a type of elliptic curve. What is an elliptic curve? Well, here's a definition. An elliptic curve, now I'm going to be talking over Q, over the rationals, is a smooth curve. When I say smooth, I mean that when you draw it, it doesn't have any kinks, it's continuous. You don't have to take your pen off the page, and it doesn't have any overlaps. So a nice curve. And it's given by an equation of this form. Y squared equals x cubed plus ax plus b. And what varies are these coefficients, a and b, and these have to be rational numbers. Now, En, the curve we were looking at, is precisely of this form, with a being minus n squared and b being 0. So it's En, the curve we just saw, is a special type of elliptic curve. Here are some examples. On the left, we have actually the curve E1. And on the right, we have another example of an elliptic curve. Now, they're always going to look like this, either a circle and a line or kind of like one line. And you can see why they look like this because the right-hand side of our equation is a cubic. So if you want to know why they look like this, you would plot the positive points of your cubic and then reflect in the x-axis. That's why these curves look like this. Rational points. I've already discussed a little bit about rational points. So here's the equation of our general elliptic curve. And the point is said to be rational. We've kind of seen this already. If the point lies on the curve, meaning the coordinates satisfy the equation, and it's rational, so the coordinates should also be rational numbers. And I write E parentheses Q for the set of all rational points. Here's an example. Y squared is x cubed plus 17. It looks like this blue curve here, you can see on the picture. And there are two rational points which I've marked, or which somebody on the internet has marked for me on the curve. And you can check that, for example, Q, the point 2, 5, satisfies the equation because 2 cubed plus 17 is 25, which is 5 squared. So we understand a little bit about rational points, or at least we understand the definitions. But what's maybe very surprising is that the set of rational points is not just a set. It is actually a group. So let's take 2 points, P and Q, and ask what is P plus Q? And I've written a funny type of plus sign here. The reason being that you're not just adding the coordinates of the points, because that wouldn't give, in general, another point on the curve. The way we add points, the way we define our binary operation for our group, is using a kind of weird construction. It's this geometric construction. And I'm going to briefly explain how it works. It's not, for the purposes of today, it's not very important. The important thing is to know that we do have a group structure on the set of rational points. But let's see how it works anyway. Let's take 2 points, P and Q, on our elliptic curve, and let's draw a line between the points P and Q. This will intersect our curve in a third point, R. It'll intersect in a third point because the right-hand side is a cubic. And then what we do is we reflect the point R in the x-axis, like on this diagram. And that gives us our point P plus Q. And I'll stop using this funny plus sign now. When you see the plus, that means addition in this weird way. Let's see another example. Let's say we have the point P, and we want to understand what the point 2P is, or P plus P. Well, this is a little bit different, but maybe quite natural. We draw a tangent line at the point P. This will intersect the curve in a third point, and then we reflect that point in the x-axis, just like somebody has done on this diagram. Again, these diagrams are not mine. I've lifted them shamelessly from Wikipedia, I think. And that gives us our point P plus P. Great, so we know how to add. Obviously, I haven't proven that this gives us a group, but this is what gives us a group. But, I mean, I've left out something huge. I've left out what the identity of the group is. This is one of the most important things. And if you look at these kind of diagrams with these chord and tangent constructions, it's not clear what the identity is. And why it's not clear is because the identity doesn't live on the diagram. Now, I'm going to write 0 for the identity because it's an additive group, and so we're going to denote the identity by 0. But I'm also going to denote the identity by infinity. Why is this? Well, it's because the identity, infinity, or 0, floats both above and below the diagram, which sounds pretty crazy, but it's kind of a really good way of actually understanding how the identity works. Now, if you've seen some projective geometry, it's called infinity because this is going to be a point at infinity on the projective plane. But if you haven't, then don't worry. We're going to look at these diagrams like we had before, and we're going to picture infinity as kind of like a boundary, both floating above and below the diagram. Let's try and make some sense of this. So let's look at the diagram on the left-hand side, and I want to add P and Q. Well, let's proceed as usual. I draw a line between P and Q, and I ask, well, what's the third point that this intersects my curve in? And I see, well, actually, it doesn't intersect the curve in a third point, but it does at infinity. So you can imagine it floating above, and it's going to intersect the curve at infinity. And then we reflect, I say reflect infinity in the x-axis, and that takes us to a point floating below the curve, which is still infinity. We've completed our construction, and so P plus Q is equal to infinity, or P plus Q equals 0. The diagram on the right-hand side is the same kind of thing. You can imagine P and Q kind of becoming infinitely close to become a single point, and then you would say that twice P or P plus P is infinity, or twice P is 0. Let's look at a third example. Let's go back to the diagram on the left-hand side, and I want to ask, what is P here? What is P plus infinity, or P plus 0? Now, if our additive identity is any good, we should have P plus 0 equals P. Let's check this. We take P, 1 point. We take infinity, our other point, which is floating, let's say, above, and we draw a line between P and infinity. This will give us a straight line, a vertical straight line, the same line drawn again in this diagram in blue. And you ask, well, where does this intersect the curve? It intersects the curve in a third point, namely Q. And then, as usual, we reflect Q in the x-axis. Reflecting Q in the x-axis takes us back to P. And so we get that P plus 0 equals P, which is exactly what we wanted. Maybe one last thing to note is going back to the diagram on the right, we saw that twice P was 0. If you like, P has order 2 in our group. And you can actually see that the only time we're going to have P being order 2 is when P is this point. Because if we want P to have order 2, we need the tangent line at P to shoot straight up, to be a vertical line. So I guess that's a very brief summary of how this group law works. It's more for interest because it's not so important for today, but this is how we make the set of rational points into a group. Now, I haven't checked it's a group. I haven't actually done this formally, and I haven't shown associativity, which is important. But what we can see is that this is an abelian group. From the construction, by drawing a line between 2 points, doesn't matter what order we take our points in. So this group is abelian. What isn't obvious is that not only is this an abelian group, but it's a finitely generated abelian group. And this is known as a theorem, the Mordell-Weil theorem. What does finitely generated actually mean? Well, for our purposes, it means it has the following structure. It means that the group consists of 2 parts. The group consists of a finite part, which I'm going to write EQ tors, and TORS here stands for torsion. And it's going to have an infinite part, which I'm going to write Z to the power R, which just means it's the infinite part. Now, what do I mean by all of this? Firstly, let's just note that R, the number appearing here, is called the rank of E, and that'll be important later. Now, let's look at these different parts. Well, EQ tors, this torsion part, or it's actually a subgroup, this torsion subgroup consists of all points in our group which have finite order. So any point P, such that when you add P to each other enough times, or let's say M times P for some integer M, we get back to 0. So that's the torsion subgroup. It's the finite part. It's all those points which have finite order. And then the infinite part, as I say, is Z to the power R, where R is the rank of E. Why do we know it looks like this? Well, that's what all finitely generated abelian groups look like. They all have a finite part and an infinite part. One thing to note is that if this rank, if R is equal to 0, then there is no infinite part, and so the whole group is the torsion part, the finite part, EQ tors. One final thing to note, and this is kind of what I referred to at the end of the last slide, is that if P is a rational point on our curve, then P has order 2, meaning that basically the tangent line at P is vertical, if and only if P, our point, lies on the x-axis. So a point has order 2, if and only if its y-coordinate is 0. And that brings me to everything I wanted to say about elliptic curves. So again, I'm going to leave this slide up and take a short kind of 30-second pause, help you absorb this information and see if there are any questions about this stuff as well. And also I'm going to take a drink. Just going to check the chat. Okay, nothing. Okay, so maybe let's move on. And I want to reformulate our main theorem. This was our main theorem, version 1. If we think back, it told us that n was a congruent number if and only if we have a rational point on what we now know is an elliptic curve, En, with non-zero y-coordinate. And we just saw at the end of the last slide that a point has order 2, i.e. p plus p is 0, if and only if the y-coordinate of our point is equal to 0. And this allows me to reformulate this main theorem v1 to give me main theorem v2, which says that n is a congruent number if and only if there exists a rational point on our curve, which isn't the identity, so it's not infinity, with the order of p not equal to 2. Why are these equivalent? Well, a non-trivial rational point with order not equal to 2 is precisely a point p x comma y with non-zero y-coordinate by this fact that a point has order 2 if and only if y equals 0. So using this size of p or order of p is 2 if and only if y equals 0, I've simply rephrased my main theorem v2. I've rephrased main theorem v1 to give me main theorem v2. And at this point, maybe you think, it doesn't look like a very nice statement. I don't really like it. But we are stating this more in terms of the group structure. But if you really don't like it, don't worry, because I'm about to restate it again. And what I'm going to first do is give you a proposition. I'm going to call this the torsion proposition. So remember, the torsion part of the group ENQ are the points of finite order. And my claim is that there are precisely 4 of them. Well, actually, we already know 4 points. We know that infinity, our identity, is a point of finite order. It's got order 1. And we know that 0, 0, n0, and minus n0, which are all the points of order 2, also have finite order. And what the torsion proposition says is that for our specific curve, En, that those are all the points of finite order. And what this does is that it allows us to rephrase our main theorem. So this is what V2 told us. This was on the last slide. And now this is what V3 tells us. It says that n is a congruent number if and only if the rank, which was the measure of how big the infinite part is positive. So let's give a quick proof of this, although it kind of follows from the torsion proposition above. So let's take n to be a congruent number. Then by V2, by theorem V2, this tells us that there exists a non-trivial point in our group with order not equal to 2. But then by the torsion proposition, if it's A, non-trivial, and if B, its order is not 2, then it can't be a point of finite order. So it must be a point of infinite order. If there is a point of infinite order, it means we have an infinite part, and so the rank R is bigger than 0. And then conversely, it's pretty much the same thing. If the rank is bigger than 0, we have a point of infinite order. So there exists a non-trivial point with order certainly not equal to any finite number, so not equal to 2 in particular. And so n is congruent by our main theorem V2, which proves that. So that proves main theorem V3 if we assume this torsion proposition. And the next aim is going to be to prove this torsion proposition. So I'll leave, this is quite a short section, so I'll just take a short moment to let you absorb in theorem V3 and this torsion proposition, and then we'll go on and try and prove this. Just check to see if there are questions in the chat. No, I don't think so. So let's go on. Torsion. This is our torsion proposition. It tells us that the size of the torsion subgroup is 4. Now this section, this fourth section, is going to be the kind of the most difficult of the talk. So it's just going to be proving this. And if you don't follow, if it's a bit tricky, don't worry too much. Hopefully when we come back to the fifth section, the BSD conjecture, the level will become a little bit more accessible. So I'm going to go slightly faster through this section. So don't worry too much if you can't follow. I'm now going to work not just with an elliptic curve with coefficients in the rationals, but I'm going to take my coefficients to be whole numbers, integers. So A and B are going to be in Z. And there are two main theorems which I want to use here, which are very classical theorems in the theory of elliptic curves. The first is that if I have a point of finite order Q, then a priori, all we know is that its coordinates are rational. But actually, what Lutz-Nagel tells us is that its coordinates are integers. That's quite an easy fact or theorem to state, but it's important. The second one is the second one is more complicated to state. It's called the reduction theorem. And it says that fab fm primes p, now I know that sounds like the name of a pretty crappy radio station, but it actually means for all but finitely many. I want to use this a lot, so I've put this abbreviation in. For all but finitely many primes p, these are rational primes, usual prime numbers. E bar, now E bar, I'm going to explain this theorem in more detail on the next slide, but I'll do it also as I go along here. E bar, which is reduce the equation of E modulo P. Whenever you see a bar, it means reduce mod P, is an elliptic curve over FP. And I have a map which goes from the torsion subgroup to the FP points of E bar what this map does is it reduces my coordinates modulo p. And what the reduction theorem says is that this map is not just any old map, it's an injective group homomorphism. Now I'm going to repeat this reduction theorem on the next slide. Here it is, stated again in a slightly shortened form, and I want to go over the different parts of this theorem. Firstly, FP. Most of you are probably familiar with this, but those of you maybe in first year won't have seen it, or maybe in second year won't have seen it. This is your Z mod PZ. It's going to be your finite field with P elements, the integers mod P. E bar, I mentioned this. This is the same equation as before, but A and B, we've reduced them modulo P. When I say E bar is an elliptic curve over FP, it means that it's smooth. Now, smooth doesn't make as much sense as before. Before, we could just draw it and say, oh, smooth means it's continuous, no kinks, no overlaps. Here, smooth is a more technical condition, but there is a way to make it make sense, if you like. And so when I say it's an elliptic curve over FP, I just mean that it's given by an equation with coefficients in FP, and it satisfies some technical smoothness condition. When I write E bar FP, this should be hopefully a clear definition. It's all those points living in the finite field FP, or whose coordinates live in the finite field FP, which satisfy the equation of E bar. And I have again this problem, or I need to include, again, this is a group, I need to include this additive identity. So I need to include infinity bar. And the set is finite, right? You only have finitely many choices for X and finitely many choices for Y. And so we certainly only have finitely many FP points on our elliptic curve. When I say FP points, it's just like saying rational point, but with Q replaced by FP. Now, what's really the consequence of this reduction theorem? And you can at this point forget the reduction theorem and just focus on the consequence. Well, because this map is injective, the size of the image is equal to the size of EQ torse, the size of the domain. And because this is a group homomorphism, what Lagrange tells me is that the size of the group, the size of the subgroup, divides the size of the group. And so the size of the torsion subgroup, which is equal to the size of its image by injectivity, is going to divide the size of the whole size of the whole group E bar FP. And again, this is by Lagrange and injectivity. And this is going to hold for all but finitely many P. Now, let's have a look at a quick example. Let's look at E7. This is I've just substituted n equals 7. It's given by this equation. And let's take little p to be 5. Then I can reduce modulo 5. I get the same equation out, but minus 49 becomes 1 modulo 5. And so it's y squared is equal to x times x squared plus 1 bar. I have the point 0, 7 living on my curve E7. This is one of the points on this curve. And then what I want to do is I realize that 0, 7 here, if I set, this is not going to be a point on the curve because I realized that I've messed things up and this should be 7, 0. So I apologize for that. This is one of our points of order 2. So this should be R5 in parentheses 7, 0 and not 0, 7. Anyway, I reduce this modulo 5, and R5 is simply reducing the coefficients of this modulo 5, and that gives me a point on E7 bar, and the point, its coordinates live in F5. So excuse the typo there. Now, let's try and prove our torsion proposition. It's going to be in 3 steps, and this is going to be the hardest part of the talk in terms of difficulty of the maths. I want to prove that I only have 4 points of finite order. We already know we have 4. So let's suppose for a contradiction that we have more than 4 points. More than 4 points of finite order, I should say. Then either we have a point P of odd order M, that's one possibility, a non-trivial point of odd order m, or every p, and I should say, which has finite order, has even order. So either we have one of odd order, or every one which has finite order has even order. And, well, if we have a point of odd order m, if we're in this first case, then we can look at the subgroup it generates. That's going to be a subgroup of size m. If every point of finite order has even order, then it turns out, you could see this using what finitely generated abelian groups look like. You could see that the torsion subgroup has a subgroup of size 8. Alternatively, if you've seen Silo's theorems, this is immediate, but you probably haven't. But you could see this using the classification of finitely generated abelian groups. So we have a subgroup S of size m. M is either odd or m is 8. Now, by Lagrange, again, m, the size of our subgroup, divides the size of the group. And by the consequence to our reduction theorem, this in turn divides the size of En bar Fp for all but finitely many primes p. And so skipping out the middle term, I get that m divides the size of En bar Fp for all but finitely many primes p. So I've repeated that on the next slide. This is step 1. That's what step 1 has told us. Let's go on to step 2. My claim is that the size of En bar Fp, the thing that m divides, is equal to p plus 1 for all but finitely many primes p which are congruent to 3 mod 4. So look at every prime p which is congruent to 3 mod 4, and I'm saying that for all but finitely many of those, the size of En bar Fp is equal to p plus 1. Why is this? Let's prove the claim. Let's reduce our curve mod p, and I want to count points. Well, I have 4 distinct points, at least for all but finitely many primes p. I'll have these 4 distinct points, infinity, and the reduction mod p of the 3 points I already know. Now, this is the trickiest part of the argument. I'm going to take x, which is going to be a point in Fp, but not 0, n, or minus n. And I want to consider the set x and minus x. And my claim is that for each of these sets, I get out 2 points. Why is this? This follows because my right-hand side of my equation is an odd function, and because p is congruent to 3 modulo 4. Now, let me say a little bit more about this right away. What I mean is that because this is odd, it means that when I put x into the right-hand side, and when I put minus x into the right-hand side, I'll get the same thing, but they'll differ by a sign. So one of them is going to be x squared minus n bar squared, and the other will be minus that. And now, because the prime p is congruent to 3 mod 4, if you've seen anything, say an introductory number theory course, you'll have seen that the squares modulo p, when p is congruent to 3 mod 4, precisely one of plus z and minus z will be a square. So precisely one of these will give rise to a non-zero square, and whichever one it is will have 2 values of y which will square to give what we want, and so we'll get out 2 points. So maybe this is certainly the trickiest part of the argument, and maybe go back over this if it doesn't make sense, or maybe ask some questions at the end. What it tells me is it allows me to count my points. I have the 4 points that I already know, and then I have for each of these sets, x comma minus x, or minus x comma x, well, I have p minus 3 over 2 of these sets, and for each one, I have 2 points. So the number of points is 4 plus twice p minus 3 over 2. And I see I have a question, so let me just jump to that. Thanks for asking. Where did you get x squared from? We only have x in the equation of the curve. So in the equation, you're completely right. So thanks a lot. That is, I'm afraid, another typo. So thanks a lot for pointing that out. It should say x times x squared minus n bar squared. and minus x times x squared minus n bar squared. So yeah, thank you for pointing that out. Another typo, I'm afraid, but you're completely right. I've just substituted x and minus x in, so I shouldn't have these squares at the start. So thanks for that. But I have counted my points, and I found that I've got p plus 1 of them, which is exactly what I wanted. And this proves my claim. So I can now substitute this in to step 1, and what it tells me is the following. It tells me that m divides p plus 1 for all but finitely many primes p congruent to 3 modulo 4 with, as we know, m is either 8 or m is odd. And let's look at the cases. Well, firstly, let me state something equivalent to this. All I've done in this equivalent statement is I've replaced m divides p plus 1. I've replaced that by p is congruent to minus 1 mod m. That's the same statement, but with just that changed. Well, let's look at m equals 8 as an example. M is either 8 or odd. If m is 8, then what this tells me is that I only have finitely many primes p congruent to 3 modulo 8. Why is this? Well, let's take a prime p congruent to 3 modulo 8. If it's congruent to 3 modulo 8, then it's also congruent to 3 modulo 4. And the statement above tells me that for all but finitely many of these, p should be congruent to minus 1 mod m, which is 8. So p is congruent to minus 1 mod 8, almost always. And so I'm only going to have finitely many primes p, which are going to be congruent to 3 modulo 8. And you do a similar thing in the other cases. I'm not going to go through them, but it's the same type of argument. If m is odd, we split into two cases, when 3 divides m and when 3 doesn't divide m. And you get out similar statements, that there are only finitely many primes p congruent to something mod something else. And this is an issue, because in all three cases we contradict the very well-known theorem, Dirichlet's theorem on primes in arithmetic progressions. What does the theorem say if you haven't seen it before? It says that there are infinitely many primes p congruent to a mod b whenever a and b are co-prime. So whenever the greatest common divisor of them is equal to 1. And you can see in these above three examples that the greatest common divisor of 3 and 8 is 1, of 7 and 12 is 1, and when 3 doesn't divide m, the greatest common divisor of 3 and 4m is 1. And so in all three cases, we have a contradiction, and we conclude that the size of the torsion subgroup wasn't bigger than 4 and was actually equal to 4, which proves our torsion proposition and brings me to the end of this section. So again, I'll take a pause now. The last section is only 2 slides long, so I'll wrap it up fairly quickly, but maybe I'll leave this up for a moment, take a short pause, and ask if there are any questions at this point. Obviously, I'm almost done, so there'll be time for more questions at the end as well, of course. I'll just check the chat as well. Right, so maybe I'll go on, and let's look to see how this ties into the BSD conjecture. So this is what this was, which now that we've proven our torsion proposition, we've kind of justified this reformulation, main theorem v3, which says that n is a congruent number if and only if the rank of En is positive. And how do we test if the rank is positive? Well, it turns out that actually for small values of n, we can already do this. We don't need this BSD conjecture. Now, when I say small, I probably mean different to your small. So my small and your small probably aren't the same thing, because here when I say small, I mean up to about 500,000. So maybe not your idea of small, but up to about 500,000, we already know how to do this, or we can computationally do this. But for large n, so let's say n equal to 1 million, we don't know how. Unless we assume this Birch and Swinnerton-Dyer conjecture. So let's try and state this conjecture and see how it links in the last 2-3 minutes, how it links to main theorem v3. I need to give one definition before I can do this, and it's the L function or L series of an elliptic curve. Let's take E, an elliptic curve over Q. Then I want to define a function. The function takes a complex number S and it takes it to this infinite product over primes. It doesn't really matter what it does, it's a function on the complex plane. In fact, it's a function on the complex plane only for those numbers which have real part bigger than 3 over 2. So it's kind of like a function on the right-hand side of the complex plane. As I say, it's not really too important what it is. There are two things in this definition which I haven't defined. One is AP. It's given by P plus 1 minus the size of E bar FP. And the other is delta E, which is given by this formula here involving the coefficients of my elliptic curve. That's what it is, not too important. And as we just said, or as I just said, this is defined for complex numbers S whose real part is bigger than 3 over 2. But, and this is due to Wiles, the same guy who proved Fermat's last theorem, it turns out that you can actually make this definition work to the whole of C. Why doesn't it work already for the whole of C? It's because this product over infinitely many primes doesn't converge. But via a process called analytic continuation, we can actually extend it analytically to the whole of C. So we have this function, it only works on part of the complex plane, but by proving some really hard stuff, we can show that actually we can make it work for the whole complex plane. And this allows me to state the Birch and Swinnerton-Dyer conjecture. I've extended it to the whole complex plane, so I can certainly talk about its value at 1. And what this conjecture says is that if I look at its Taylor expansion about the point 1, it has this form. Here, C is a non-zero constant, and R is the rank of E. So the Birch and Swinnerton-Dyer, which is conjecture, as I say, it's a conjecture, we don't know this, but we think it's true. It says that its Taylor expansion looks like this, which looks like, for such a big conjecture, it doesn't look like it's very important, but the consequence is, this is the last thing I'm going to say really, is that the rank of E is going to be positive if and only if the L function evaluated at E is, the L function of E evaluated at 1 is 0. Why is this? Well, let's suppose the rank R here is positive. Well, you can see when you chuck in S equals 1 into this Taylor expansion, everything's going to disappear. And so L of E at 1 is 0. And conversely, if L of E at 1 is 0, that means that this R, this rank, better be 0. Because if it were better be bigger than 0. Because if it were equal to 0, when you chuck in S equals 1, you would get out C, which is non-zero. That would be a contradiction. And so this consequence of the Birch and Swinnerton-Dyer conjecture is really what we're interested in. What does it allow us to do? It allows to restate main theorem V3, because we have that n is congruent. This was main theorem V3. N is congruent if and only if the rank of Vn is bigger than 0. And by the Birch and Swinnerton-Dyer conjecture, this happens if and only if the L function evaluated at 1 is 0. And this is something we can test, and we can test it for really, really big n. And so if we can prove the Birch and Swinnerton-Dyer conjecture, or if you can prove the Birch and Swinnerton-Dyer conjecture, then we have a way of testing whether a number is congruent for really large values of n. And so that's all I wanted to say. I've left a kind of a summary of the logical implications that we've been through throughout this talk. Maybe I'll first say thank you very much for listening. Thank you for coming. And I'll flip back to this slide, leave it up, and I'll stop speaking now. I've spoken for long enough.